On the last video, we asked you to think about what you're doing in this problem. Minimizing, what you're actually doing is minimizing the product of the fault displacement and the length of the fault cut rather than the work, since this is really just this is kind of an oversimplified view of what the work is that's required to produce this fault. So hope you spent a little bit of time thinking over that question and what you were trying to minimize. And you might recall just from seismology if you've had it, but basically the energy that's released by an earthquake or by a fault that ruptures on which you have some displacement is equal to the seismic moment times the static stress drop divided by the shear rigidity. There are other relationships. I mean, basically the seismic moment is just another measure of energy release, and it's proportional to the product of the area of the fault which has been ruptured and the displacement along the fault times the shear rigidity. So this is really a different problem, and we came up, in the last video we came up with 45 degrees as the angle which minimizes the product. And I'm kind of rephrasing this because this is effectively what we're trying to do, is minimizing the product of L times M. But my question is, does it really minimize the product of L and M? So let's come back and take a look at the formulation of the problem. We noted that we could define M as E over the cosine of theta, and L, the length of the fault cut, is equal to T over the sine of theta, so that we were minimizing this relationship here, the work being proportional to the product of L times M. And, again, these are our L and our M. Now, what we could do is express M as delta Z over the sine of theta. So let's take a look at that. In this case, sine of theta is equal to delta Z. This would be our vertical displacement here, over M, side opposite over the hypotenuse. That gives us that M is equal to delta Z over the sine of theta, and L is equal to T over the sine of theta. So instead of the cosine of theta and the sine of theta, in the denominator we have sine of theta times sine of theta. Okay, so over here, kind of the vertical drop in this layer, delta Z, with M, the length of the fault cut, being proportional to delta Z over sine of theta, and L to T over the sine of theta. We end up with these two different approaches. The approach that we went through on the last video, we minimized this function, and this formulation here, where we re-express M as delta Z over the sine of theta. So we still have these constants, alpha, T, and delta Z. Now, I cheated and I went to Wolfram alpha, and we went through this derivative the last time. We saw that it's 0, the first derivative is 0 at pi over 4. That's at 45 degrees, and we showed that, that in fact, when we take the second derivative of that function, that we have a minimum there at pi over 4, and it's positive. So that tells us that the product of L and M is a minimum, or at least it suggests that it's a minimum at 45 degrees. So that's using this approach 1 that we went through, where we have the work expressed as a constant over the product of the sine of theta and the cosine of theta. In the second approach, we have a constant over sine squared of theta. So in approach 2, again, just using Wolfram alpha here. We're minimizing this function here. We take its derivative, 1 over sine squared of theta. We get this function. We see that it is 0 at pi over 2. In other words, is this function a minimum or a maximum? We don't know yet. Its derivative is 0 at 90 degrees, not 45 degrees. So we've got a 0 slope at 90 degrees. Now taking the second derivative, if we look at the value of the second derivative at pi over 2, it turns out to be equal to 2. So following these two different approaches, depending on how you define m, the length of the fault cut, not the length of the fault displacement, m, you come up with two different solutions, and we could probably go in there and express L as a function of the cosine, and then have cosine squared in the denominator. But you can see that we have two possible solutions here, two possible approaches to minimize the product of L times m. And in the first approach, we found that theta, in order to minimize this product, would be 45 degrees. In approach 2, we find that it's going to be 90 degrees in this case. So, and I think you can see that just visually. If you thought about this, if you thought about minimizing the product of L and M, the product will be minimized when both M and L are at a minimum, and both M and L will be at a minimum when theta is equal to 90 degrees, and we just have a vertical fault. So this points out, maybe you can get some contradictory answers from, depending on how you formulate the problem. But again, I would point out that this product of L times M really doesn't accurately reflect the work involved. And so take a quick look at a couple slides from some of Zobac's work. When we have normal faulting, we have the vertical stress is greater than SHmax, which points along the strike of the fault, which is greater than SHmin, which is oriented perpendicular to the fault. In order to get normal fault displacement, the vertical stress is the largest stress. And we also know that we should be doing things like using more circles and looking at stress differentials, the maximum and minimum stress, and considering the coefficient of friction plus the cohesion along the fault, and going about the computation of a fault angle, or the range of fault angles that you might see in an area with a given stress distribution, using this traditional Mohr circle analysis. So faults generally are steeper than 45 degrees, and the angle that they make with SV is usually around 30 degrees. So this 60 over here would be twice the angle made with the vertical. So a couple takeaways there is that there are different ways to look at there are several ways to look at this problem. If we just look at trying to minimize the product L and M, we came up with two completely different solutions. And if we really want to talk about what the fault angle is that minimizes the work, and you're going to be coming back to more circle relationships. But this has been a good example of how to use derivatives to locate minima or maxima, and second derivatives in order to determine whether those locations are minima or maxima. And thanks for joining me. Hope this was useful. We'll see you in the next video.